All right, guys, part 2 of the related rates intro. Another question, a hypothetical square. That's a weird way to start this, but it's a square and it's shrinking at a certain rate. And you can look and you're like, this is a rate of change of area because it's given in meters squared per minute. So this is like an A, an area, and this is a T, a time. So I'm looking at this, and the first thing I do when I see 36 meters squared per minute, I say dA dt equals negative 36. And it's negative because it says shrinks. It's getting smaller. So the area is decreasing. Then it says at what rate are the sides of the square changing? So you don't have to draw a picture for this one maybe, but you can. Here's a square. And its area, if the side is called S, the area we find by doing S squared, S times S. And so this is going to be the equation that relates, well, so it says at what rate are the sides of the square changing when the sides are 8 meters each? They want ds dt. S, if you call this side S, you can call it X or K or whatever you want to, but I call it S because the word side begins with the letter S. So it helps me remember what it is. And this is what they want me to find. At what rate are the sides changing? So ds dt is what? And I'm going to write this up here so that we know that this is the time, this is the side length at which I'm interested in this answer. We're not going to plug this in yet, but we're going to know that after we take our derivatives with respect to time and get our rates, we're going to plug in this s equals 8 to find the rate that we're looking for. So we write down our equation, a equals s squared. This was step 1. What the hell was step 2? Let me remind myself. Find an equation. We did that. Boom. Right here. 2. Step 3, I assume, was to take derivatives. It was. So I'm going to do derivative with respect to time of both sides of this equation now. A equals s squared. The derivative with respect to time of A is dA dt. Technically, it's 1 times dA dt, but I generally don't write the 1 because this is just the variable A. Its derivative is 1 times the derivative of A, dA dt. Now I have the derivative of something squared. The something here is S. And the derivative of something squared is 2 times the something times the derivative of the something. That last part is the chain rule. It's implicit differentiation. So I do 2 times the something times the derivative of the something. Like I said, I want you guys to be writing the d over dt notation for these and not the s prime, because s prime is not as intuitively interesting as ds dt. So now I have this rate, which they gave me. I have this rate, which I'm looking for, and I have a side length here, which they say when s is 8. So dA dt is negative 36. S is 8. 2 times 8 is 16. And then I have ds dt. This is step 4, I think. This was step 3 here. This is step 4. Solve for this. I divide both sides by 16. I think that's negative 9 over 4. And now the 5th step in my mind is to write down the unit for this. And you can kind of look back at this expression to figure out the units. ds is a change of s, and s was measured in this one in meters. I can see it up there for the area. It's meters squared. So this is going to be meters per, and look at the bottom is time. And the time unit in this one was minutes. So it's meters per minute. Meters, that is real messy. Meters per minute. So you pull the units out of the problem. It tells you what the units are supposed to be. Meters per minute. That's how we do these. This is your answer. It's not so bad, right? Negative 9/4 meters squared meters per minute. So that's an example. I can do one more, I suppose. And maybe I'll talk about this last one here in class. This was a part of from an AP test, so I'll probably talk about that one in class. But it's not that much different from the other ones. This one looks a bit like the first one. It's talking about a circle. a circular pool. And this time the radius of the pool increases at a rate of 2 centimeters per minute. So this is my given rate here, 2 centimeters per minute. And so I would write that down, since it's the radius that's increasing, I would write it as dr dt, rate of change of the radius per time. And that is 2 centimeters per minute. It's probably a good idea to write these units down so I don't forget what they are halfway through the problem. This time, the rate is positive because the radius of the pool is increasing. This means a positive rate. The radius is getting bigger. So as time changes, the radius increases. I want this to be positive. And then how fast is the area of the pool increasing? Well, that's going to be the rate of change of area per time, dA dt. Rate of change of area over rate of change in area over change in time. That's what I'd like to know. And the time, the moment at which I want to know that is when the radius is 5 centimeters. So this one, we actually already did one with a circle. So we maybe know this was step 1. Step 2 is to remember that the equation that relates the area and the radius is A equals pi r squared. So the third step is to take derivatives with respect to time of both sides. So d over dt of A equals d over dt of pi r squared. I wrote the 2 this time. I guess I could have written the 1 with the parentheses like I did before, but it's the same thing. This is probably technically more correct, but it doesn't make any difference. As long as the next step says this, dA over dt, which is the derivative of area with respect to time, technically times 1, but I'll always write that, equals, and we saw this derivative already. This is a constant multiple, so I just leave it there. The derivative of something squared is 2 times something, in this case 2r, times the derivative of r, which is dr dt. So this is I've taken my derivatives now, which means it's time to start plugging things in, which of course is step 4. The rate of change of area, they don't tell me. That's what I'm looking for. So this is actually going to require less algebra at the end. Just going to rewrite that. Pi is just pi, 2 times r. In this case, r is 5. So 2 times r is going to be 10. 10 pi times dr dt, which they gave me is 2. Which means that the derivative of area, the rate of change of area with respect to time, is 20 pi. And now my last step is to write down the units. This is a rate of change of area over the rate of change in time. Area in this problem is measured in, well, the unit length is centimeters, which means the area is going to be measured in centimeters squared. And the time is measured in minutes, so it's going to be centimeters squared per minute. And this will be your answer. 20 pi centimeters squared per minute. The nice thing about putting the pi's in those area numbers is that it makes everything kind of works out better. The numbers work out better if you do that. That's why those are always in there. So that's how we do these. Write down the things we're given, write down an equation that relates the rates, take derivatives with respect to time, plug in the things we're given, solve for what they were asking us to solve for. And here is a 6-step process because they added this sketch a figure, which we kind of did. We did that on the square one just so we could kind of see what it looked like. Find the rates that you're looking for and the ones that you're given. Express them as derivatives. We did this in one of them. Find the equation. This was really our 2nd step, I think. This was our 3rd step. This was our 4th step and 5th step. And then remember, I said I want you guys to include units in your answer. This is important. I'm just going to I'll tell you right now, there's going to be points on every problem that we do with these for the units, and I'm going to take off every time you don't put them on there. So make sure that you do. And like I said, I think this one is included in the notes I gave you. If it's not, we'll talk about it in class, but this is, like I said, it's a little trickier because there's a product rule in here and I want you guys to see me do that. kind of in person. You can ask questions if you need to. But I hope you guys learned something, and I'll see you in class.